Welcome to APA's weekly webinar. My name's Billy Sadek, Manager, Special Projects for APA. Just a couple of housekeeping items before we get started. The webinar recording will be posted to the APA webpage later this afternoon. You'll receive a follow-up email in the next couple of days with a link to the webpage where all webinar recordings are housed, as well as links to our upcoming webinars. We have webinars planned out through the end of the year, and many are open for registration. Professional continuing education and AIA-CLU credits are being offered for today's program. If you are an AIA professional requiring a certificate, please send an email to me at Billy, B-I-L-L-I-E, @APA.org, along with your AIA membership number if you have not done so in the past. All attendees are in listen-only mode. Please type your question in the chat box and they will be answered in the order they are received. If we run out of time and we still have questions, responses will be sent directly to the person asking the question by our presenter. At this time, it is my pleasure to turn this over to Chris Glover. Chris, take it away.
Great, thank you very much, Billy. Hopefully everyone had time to read the opening slides here. I'm going to go over the learning objectives in the course description in a few minutes. Just want to briefly thank you all for joining in today. Have quite a bit of information to share with you all, so I'm going to kind of dive right into it. For those of you who don't know me, my name is Chris Glover, and I am the Director of Energy Recovery Restoration, which is really just a fancy way of saying I work with folks who keep buildings operating. Air Exchange is an energy recovery provider. We're going to have a lot of discussion on that technology. And if you've never sat through one of my webinars before, the way I try to develop the narrative is to kind of attack or kind of go after the narrative from many different angles so that regardless of your background, everyone walks away with a little bit more information. Okay, so really quickly, just a little background information on who we are. Air Exchange was founded in Rockland, Massachusetts 40 years ago. For those of you who don't know where Rockland is, it's just south of Boston, Massachusetts. We have over 300,000 energy recovery components in the market, and that is growing. We are a charter member of the ASHRAE EERV committee. We are a member of the ASHRAE 90.1 mechanical subcommittee. We are a member of ASHRAE 62.1, the ventilation committee, and we are a member of TC55, which is the energy recovery committee. We're currently the largest OEM component supplier of energy recovery components in North America, and all of our products are ASHRAE 1060 certified for performance. Okay, so prior to beginning the discussion, I just want to point out that the focus of this presentation is going to be general ventilation and energy recovery guidance and not specific to the system design. The current state of HVAC in schools varies quite a lot across the country, so every location in their facility is going to be a little unique in their own regard. So as we begin, it's also worth noting that schools and universities are the largest vertical market for energy recovery technology. And as you may all know, there's a large national focus and discussion on the operation of the ventilation system, but not with a whole lot being said on energy recovery. So I thought it was important to try to tie the two technologies together. So really quickly on the agenda today, we are going to have a quick overview on ventilation and the benefits of dilution. We're going to review the operational guidance that's coming from national bodies like the CDC and ASHRAE. I will then do a quick review on energy recovery technology and its operation. We will then go over the line items for inspection and evaluation of energy recovery systems, followed by how you clean and remediate energy recovery systems. And lastly, I'll end the discussion with the sources that I use and some resources that are available to you. Okay, so really quickly, let's take a look at a typical ventilation process. Outside air goes into the HVAC unit. That air then gets air conditioned to a point that's acceptable to be delivered into the space. Then the fresh outside air then dilutes the stale space air, which is then displaced and exhausted outside the building. So the main benefit of ventilation is dilution. Dilution in its very basic form is the continual reduction of concentrations of contaminants of concern. So the rate of airflow delivery into the occupied zone is typically presented in cubic feet per minute, or sometimes referred to as air changes per hour, which is essentially the rate of airflow delivery as compared to the volume of the space. But it refers to how many times per hour the entire volume of air within that space is completely replaced with fresh outside air. So dilution is the continual reduction of a contaminant source within using the introduction of fresh outside air. The generalized dilution curve that you see on the left is often used to represent the reduction based on a normalized airstream. And what it usually represents is every time you double the air changes within a space, you cut the indoor concentration of contaminants in half. This particular process has been used for many, many years to kind of demonstrate the benefits of ventilation. Now, the generalized curve is used to represent what most consider normal occupied space air, and not necessarily stemming from a viral or a health-related concern. But that's not saying there isn't a long history of studies that demonstrate a similar curve that's been used to represent health-related gains as it compares to increases of outside air. So the science behind reduced infection rates as it relates to ventilation is most often attributed to what's known as the Wells-Riley equation. Back in 1955, Wells developed a way to calculate what's known as a quanta of infection and relate that quanta to a relative risk of infection reduction. Now, it's important to recognize that the quanta is essentially what is a uniless dose of infection rate. So it's a value that people can use to correlate risk reductions in indoor spaces. So it wasn't until 1978 that Riley took the quanta and developed a risk assessment model that established an infection rate reduction with increasing rates of ventilation. And if you look at those curves, it really demonstrated that the process of risk reduction follows a very process similar to the general dilution curve with increasing amounts of outside air. Now, the Wells-Riley equation has gone through several updates over the years to include additional technologies like filtration and UV light, and has become what most people refer to now as the modified Wells-Riley equation. And the reason I'm going into such detail is that I want to demonstrate that ventilation along with filtration and UV aren't independent of one another. They're all additive, and they all hold equal weights in calculating risk reduction when you're determining strategies for what to do with the occupied space. So what determines the ventilation rate in commercial buildings? ASHRAE Standard 62 is the ventilation standard for acceptable indoor air quality in commercial buildings, and it's the most referenced standard in commercial building codes. I should state that the standard is not a health standard, meaning that disease transmission was not considered when developing the rates. It strives to provide guidance that provides health, occupant comfort, and but it doesn't guarantee it. More recently, the ASHRAE Board of Directors approved a rule stating that ASHRAE standards shall consider health impacts where appropriate. But even with that in place, those rates that are within the standard are largely based on what it takes to dilute normal sources of contaminants. So what's a normal source of contaminant? It's typically bioeffluent, which is contaminants that come from people, more often referred to as odors, and off gases from building materials or off gassing from building materials, furnishings, or processes that may be occurring in the occupied space. And with those elements taken into consideration, the standard then provides the minimum ventilation rates to achieve proper dilution. Now, you may notice I highlighted minimum because as most code-related values go, the minimum often becomes the maximum. And as demonstrated on the previous slide, some of the health-related and cognitive gains that are often attributed to higher ventilation rates than what's presented as the minimums in the ventilation standard today. So looking specifically at some sample rates for educational spaces, there really are three paths for compliance with the standard: the ventilation rate procedure, the indoor air quality procedure, and the natural ventilation rate procedure. The one that's most commonly used in the marketplace is the ventilation rate procedure, which is a function of the number of occupants and square footage. What's kind of unique to educational spaces is if you go through the standard, they represent some of the higher occupant density spaces, meaning educational spaces traditionally have higher ventilation rates associated with their spaces, which is why they're a pretty good fit for energy recovery technology. So if ventilation is so important and we have such importance in maintaining health and getting cognitive benefits out of it, why aren't we just dumping tons and tons of outside air into the space? And it's really because it takes a lot of energy to condition outside air. So if you're looking at the chart at the left, your outdoor air conditions at any given day at any point in North America can reside within that dotted line. And that's a pretty big operational window. The red dot and the blue dot represent your typical indoor conditions in both heating and cooling modes. And as you move away from the points, the bigger the energy load is going to be on the building. So essentially, the hotter it gets, the colder it gets, the more humid it gets, the more energy you're going to need to condition it. Also, the big operational window means it's going to be more difficult to design a system that can operate efficiently with all those conditions in place. So energy recovery has really been developed to respond to those challenges. The easiest way that I can describe how an energy recovery process is and works is that all the device wants to do all year long is bring the outside air condition as close as it possibly can to the indoor condition. It performs this process passively, meaning as long as there's a thermal or moisture difference between the air streams, the device is working to perform the process. A typical energy recovery system reduces the energy load associated with the ventilation air by 50 to 80%. So you can get higher efficiencies if the system's designed for it. That just happens to be kind of the market standard that we see being developed in most buildings. Once again, looking at the chart, what the energy recovery device does is shrink the operational window from the dotted line to the solid line. And the difference between those two are going to be your energy savings. Also, that reduced operational window is going to create a more ideal and far more predictable control over the air for occupant comfort. So the next section is going to cover some sources where you can find operational guidance as it relates to educational spaces. So there's a lot of fragmented information available right now, and new information is continually coming in. I'm an HVAC engineer, so I have been largely following what's being discussed by ASHRAE and CDC and other building-related communities. The guidance that I'm going to present is really the high-level messaging, high-level messaging that's coming from these sources. The specifics, though, of how you're going to accomplish that is going to vary from building to building. Starting with ASHRAE and the documents that I believe are the most important for this particular topic and audience are the following. First, you have the ASHRAE position document on infectious aerosols. This was one of the first technical pieces that was written and developed by the ASHRAE Epidemic Task Force. And its purpose really kind of set the tone, its purpose narrative, I should say, really set the tone and direction that the task force was going to take during the epidemic. The next is the core recommendations for reducing airborne infectious aerosol exposure. There's a couple of tongue twisters in here. It's a one-page document that represents what ASHRAE has determined to be the core guidance for operating HVAC systems, followed by the one-page guidance for reopening schools. Again, another one-page document with the intent to provide core information as it relates to educational spaces. The ASHRAE reopening schools and universities guidance. This is a much bigger document. So this is a 40 or 50 page document, but it really dives into specifics of what you should be looking at into those systems. And lastly, there's the practical guidance for the epidemic operation of energy recovery ventilation systems. This is the document that I'm gonna highly recommend that you read if you have an ERV system placed in your facility. And it's really intended, I was actually on the committee that wrote the narrative. It's really intended for the inspection, evaluation, and remediation of energy recovery systems during the pandemic period. So its intent is really to give building operators guidance on what they should be looking at and to make sure that they're doing their best to mitigate the potential risk. So The ASHRAE guidance is kind of largely based on mechanical operation, and that has translated over to the CDC to some effect, and they both kind of share similar guidance and reference one another. However, the CDC provides additional guidance, such as like source control, sanitizing, traffic flow patterns, and much more. But for the focus of this discussion, I'm going to focus on the mechanical operation. Okay, so I'm going to summarize some high-level key takeaways from the ventilation operation from all those documents. Really, the biggest takeaway that you're going to have is when reviewing the documents is the importance of ventilation as a means of mitigation. So ventilation with an effective airflow pattern is a primary infectious disease control strategy through dilution, which states that you're going to want to keep your ventilation system operating and optimize it to the best of your ability to achieve proper dilution. You're going to want to provide at least the required minimum outdoor air ventilation rates as specified in ASHRAE 62. Now, for some of the folks, this may be difficult, as units that operate over time have a tendency to get less efficient. This also applies to airflow delivery, and I'll speak in a couple slides on how to maximize that. If you have the ability, flush the space between occupied periods. The current suggestion or suggested rate is to provide a flush equivalent to 3 air changes. Limit re-entry of contaminated air that may re-enter the building. This includes recirculation from energy recovery devices. So I'm going to speak more to this in a few slides. And use a combination of filters or air cleaners to achieve MERV 13 or better for air recirculated by HVAC systems. Now, I highlighted recirculated air here because it requires an understanding of how air gets recirculated in the occupied space. And I'm going to talk about that in more depth in a couple of slides. All right, continuing on. You're going to want to disable demand control ventilation. So carbon dioxide is often used as a reference gas to determine occupancy. And its purpose is to minimize outside air based upon occupancy. So since most educational spaces are being used at part occupancy or no occupancy right now, you don't want the control algorithm to inadvertently lower the ventilation rate. Also, you're probably not going to want to use carbon dioxide as reference of whether or not you're achieving proper airflow. My suggestion would be to use the actual airflow of the unit and compare that to the rates being specified in 62, as carbon dioxide can be kind of a tricky gas to use to determine how the quality of the air. Increase ventilation rates above the minimum rates to maximum allowable per device without compromising thermal comfort and humidity control. This can be a little difficult, but we're going to talk about some ways that you might be able to do that. And if the building is considering replacing or designing a new ventilation unit, size the unit for 150% of the code mandated flow for periods of urgency. So this is going to help you kind of future-proof your building or your space and anticipation that anything like this would ever happen again. Just as a word of caution, looking at these core takeaways, when you're thinking about changing operating parameters of an HVAC system, there's always going to be intended or maybe unintended consequences that may arise. So just make sure you have a good understanding of the entire system effect that's going to occur before making those changes. Okay, so aside from the quote general guidance, there are prescriptive guides available specific to educational spaces. The prescriptive guides really kind of offer what I call a blueprint or a checklist that you can follow for space preparation and mitigation. The 3 that I'm going to suggest is the K through 12 COVID-19 mitigation toolkit. That was presented by the CDC, the ASHRAE reopening guide for schools and universities, and the Harvard Healthy Building risk reduction strategies for reopening schools. All of these documents are going to provide basic mechanical guidance, but only the ASHRAE guide has a section specific to energy recovery devices. So once again, if your facility has an ERV, I'm going to implore you to use that document as a way to make sure that your device is operating with what the core recommendations from the HVAC community is going to be. Oh, that was a little delayed. I apologize. That should have been in there. Give you a second to take a quick peek at that. Okay, so we discussed the operational guidance for the ventilation system. What if your system's equipped with an energy recovery device? So here's the guidance as it relates to systems with energy recovery. First and foremost, a well-designed and well-maintained air-to-air energy recovery system should remain in operation. Now you all may be asking yourselves, what does well-designed and well-maintained mean? Well, according to the HVAC community, well-designed refers to proper fan location and operating pressures, that the ERV has been sized with proper velocity and pressure drops in mind, and that the seals have been selected for the specific application. Well-maintained means that the system was installed, tested and balanced appropriately, and the building operators have been following the manufacturer's recommended maintenance procedures. And in order to minimize concern for any carryover or minimize the recirculation as the core recommendation was, we're going to discuss that in the next couple of slides in more depth. Okay, so really quickly, I'm not going to go too deep into this, but I'm going to talk about how the basics of energy recovery operation. So you may remember this slide from earlier in our conversation. We're just taking the same process and adding an energy recovery system or energy recovery component into the system. I often refer to energy recovery as a load shift, where you're essentially shifting the ventilation load from the heating and cooling element over to the energy recovery component that's using the low grade thermal energy that's just normally exhausted outside the building. So by using the low grade energy instead of a high grade energy like a gas or electricity, what it's going to do, it's going to greatly reduce the amount of energy consumed to treat the same amount of ventilation air. So you can still see that the air comes into the unit, but instead of heating and cooling the air the traditional way, you're now shifting it over to the energy recovery component. The energy recovery component is going to condition the air, which then gets delivered into the space for dilution purposes. Okay, kind of going into the different systems you see with energy recovery, it's very important to recognize the difference between the sources of recirculated air within the space. If the HVAC system just pumped outside air in and exhausted it immediately, it would be exceedingly costly to condition all that air. So, what typical HVAC system does is recirculate a portion of that air so that you can temper it so you can maintain occupant comfort. So there is a small amount of recirculation that occurs at the energy recovery component. However, the system recirculation is really going to account for 95 to 99% of the total amount of recirculated air within the space. Now, recirculated air can either be co-located, meaning the recirculated air in exhaust air is within the same duct or pathway, or it can be completely separate from the exhaust air. So rooftops and air handlers like System A often have a co-located exhaust and return air system that provide a mixed air stream consisting of both outside air and filtered recirculated air to the space. Or you can have a system like System B that traditionally uses something like fan coil units, VRFs, PTACs, which are typically only used to recirculate air. Another point of recirculation is called reentrainment. Reentrainment is essentially when exhausted air leaves the building through the exhaust damper and somehow inadvertently makes it back into the space through the air intake. And the reason that I'm going into this level of depth once again is it's going to tell you that of all the ways the air can get recirculated back into the space, the amount of recirculated air coming from an energy recovery device is magnitudes below the other sources. Okay, so if the component is ASHRAE certified, so ASHRAE 1060 is a nationally recognized standard for the certification of energy recovery components. An energy recovery component goes through a certification process just like a rooftop or a chiller or anything else to that matter. One of the values that gets certified is called EATR, or exhaust air transfer ratio. The EATR value is a percentage of the outside air, and it represents essentially how much recirculated air is being transferred from the exhaust air back into the supply airstream. Per the ventilation standard, you're allowed to recirculate a certain percentage of air. It really depends on the class of air that you're exhausting. The two levels or the two percentages that are specified within the ventilation standard are 5 to 10%, depending upon the class of air. However, if you look at most modern designs, the recirculation rates are usually below that. They're usually somewhere in the 1 to 3% area. And it's also important to keep in mind that EATR is a percentage of outside air, not total airflow. So outside air is typically the lower airflow of your total air versus your recirculated air and your outside air. So it's essentially a percentage of the smaller airstream. And when you compare that to the other airflows in the space, it's going to be pretty low. So the key takeaway is that the energy recovery system should operate as intended. Now, once again, this refers to well-designed and well-maintained, and I'm going to go into specifics in a few moments. And as we learned, the recirculated air from an energy recovery device is exceedingly low when compared to the system amount of recirculated air. So, and the benefit of the operation is going to far exceed the small but finite amount of potential recirculated air. Okay, so the next section is going to cover how to inspect and evaluate an existing energy recovery system so you can determine if the system is well designed and well maintained. So the guidance that I'm going to share here is based on the TC55 practical guidance document, which is the operation of energy recovery devices document that I spoke about earlier. It is available on the ASHRAE website, and it's really intended for building operators to use in their kind of bag of tricks as as a means to inspect and validate. First things first, safety always. Always make sure that you use proper protection equipment. In this case, it typically means masks, gloves, and making sure that you have adequate ventilation to the area that you're going to be inspecting. It's important to keep in mind that an energy recovery component is a subcomponent of a much larger system, and as such, the other components within that system are going to have an effect on the operation of the energy recovery device. So you're going to want to take that into consideration when you're doing your inspection of the system, kind of a holistic approach to the inspection. In general, you're going to be looking for items that affect pressure, as well as any potential airflow obstructions, or areas where there can be gross leakage of potential recirculated air. Now, the suggestions that I'm going to provide are based on energy recovery technologies that have airstreams that are right next to one another, which traditionally means energy recovery wheels and energy recovery plates, which traditionally is the largest part of the market. Okay, so it's important to identify your fan locations. Let me go back there. I think I passed that too quickly. As really fan position is going to determine operating pressure. Operating pressure is what drives EATR, or the recirculation, as we spoke about earlier. And this is what's going to be, and aside from operating pressure, if you have an energy recovery wheel, you do have a small amount of pumping motion between the two airstreams that can also pass air from one airstream to the other. So starting with fan location. Once again, fan location is critical for determining operating pressure. So you're going to want to take note to where the fans are located during your inspection process, because you're going to be taking static pressures in each of the quadrants that surround the energy recovery component. The three most common arrangements are displayed in the image to the left. If you find that you go through this process and you have that fourth arrangement, you should really want to contact the equipment manufacturer for advice on how to operate it during this time, as that particular configuration is prone to excessive amounts of leakage. Each quadrant is going to have its own operating static pressure, and in general, you're going to want to try to determine that the pressure scheme naturally wants the air to move from the supply side of the airstream to the exhaust air side of the airstream. So as a typical rule of thumb, you want to have roughly a ½ inch or greater of static pressure on the supply side to achieve a proper pressure gradient. With that being said, some fan arrangements provide this a little easier than others. We'll go to that in a few minutes, but and once again, when you're looking at these fan arrangements, you want to take into effect the entire system. And that's because the fan operating pressures are not only affected by the entry recovery component, but it's also affected by coils, filters, louvers, or anything else in the system that could add static pressure to the system, which would affect how the wheel operates, or I should say the component operates. Okay, so to start off the inspection process, you're going to start with cleaning the unit. Typically, you're going to use a vacuum to help facilitate the inspection of maybe difficult to get areas, and this is where you're going to look for any potential leakage. You're also going to want to clean the heat exchanger surface areas as recommended by the component manufacturer. The two most common methods employed are using either a vacuum or washing the material with soap and water. Once again, you're going to have to refer to the manufacturer's recommendations, as not all heat exchangers can be washed. For air exchange wheels, we recommend that you wash them, and I have included a section on how to perform that process that we'll go over in a few minutes. After cleaning, what you're going to do is you're going to want to check for gross leakage paths or obstructions within the system. An easy way to do this is, grabbing a hold of a flashlight and trying to shine it into different areas or sections of the cabinet and see if there's any light penetrating through. This could be through, fasteners that have been removed, or maybe even panels that may be missing due to, potential servicing of the unit over time, or really any area where you can see that where, exhaust air could be recirculated back into the building. Okay, so continuing on, you're going to want to check that the bypass or any other damper in the system is operating properly, that they're not jammed, and that all the damper seals are still in good operating condition. You're going to want to identify the general layout of the system. So, look for areas where there can be potential bypass around components. Once again, there's going to be missing fasteners, seals, really any gross leakage that could, bypass the components. Check to see if the filters are dirty. Dirty filters are going to have a significant impact on pressure and thusly airflow. Also, look for any potential obstructions. You're going to look at the filters, coils, mist eliminators, or bird screens, louvers. Anything that can get dirty or obstructed over time. So once you inspected the entire unit to see what type of relative condition it is, you're going to want to inspect the actual entry recovery component itself to see if it's operating properly. So this first part is going to be an entry recovery wheel, then we'll move over to a plate. So it's going to be a two-part process, one with the unit on and one with the unit off. Starting with the unit on, what you're going to want to determine is the wheel clean. Now you might be asking yourself, what does a dirty component look like? So it's usually pretty apparent. You'll see potential dirt and debris or potential bridging or blocking of the heat transfer media. That's a great sign that it needs to be cleaned. Then you would next want to check to see if there's any visible damage on the heat exchanger surface. And once again, what are some examples? So you'll look to see if there's any pitting or deterioration, corrosion. Is there any media missing from the design itself? So or loss of structural integrity to the design. You'll then check to see if the seals are set properly. I will say that there are two seals on entry recovery wheel, a set of seals that run along the diameter and a set of seals that run along the perimeter. So you're going to want to check both. And depending upon the wheel manufacturer, it could either be a non-contact seal or a contact seal. So you're going to want to check with the equipment manufacturer to see what type of seal you have and whether or not it's set appropriately. And lastly, you're going to want to check to see if the wheel is equipped with a purge. Now, Let me go back here. Now, you might be asking yourself, what is a purge? So if you look at that image on the left, a purge is that little triangular wedge piece that you see there. Not every energy recovery wheel is equipped with a purge, and not every application requires it, to be honest with you. But that's what it looks like. You're going to want to take the note to see whether it's a fixed plate purge or an adjustable purge. And you're going to want to take note at what setting it's at so that you can calculate your leakage correctly if that's what you're looking to accomplish. Okay, for the second part of the inspection, you're going to want to turn the system on. So the first thing you're going to want to determine is the wheel turning? Now, I know this seems trivial, but you're going to want to do this by looking at the wheel itself and not trying to rely on any type of building management system, because I've seen a lot of false positives in the past where it demonstrates that something's spinning where it actually isn't. If you have the capability to determine what the RPM of the wheel is, I would highly recommend it. A lot of energy recovery wheels are equipped with a VFD, and sometimes a VFD will override the factory settings. So check to see what the manufacturer recommends as the rotational speed and that it's operating at that speed. You're also going to want to take a note, is the wheel spinning in the correct direction? Now, this is more critical in units equipped with a purge, because if the wheel isn't spinning in the right direction, a purge may actually siphon air rather than minimize recirculated air. So once again, VFDs can have a role in this parameter, so we want to make sure that that's spinning in the correct direction. And with the system in its normal operating mode, with all the bypasses closed and the doors closed, what you're going to want to do is you're going to want to measure the static pressures in each of the 4 compartments that surround the heat exchanger. And you're going to want to do this for every operating mode if the unit has more than one operating mode. To kind of help assist with recording all this information, the TC55 document does have a sample chart that you can use to help record it. The most critical points to determine leakage and recirculation are highlighted in red. And once again, what you're looking for is a more positive pressure in the supply side of the system than in the exhaust side of the system. Depending upon how the fans are set up, you may have negative pressures on both sides of the wheel. But once again, as long as the pressure differential is from the supply side to the negatives, or from the supply side to the exhaust side, that's what you're hoping to accomplish. And you're going to use the outside airflows as a way to determine if you're receiving adequate amounts of outside air delivery into the space. Okay, so moving over to devices that use static plates. Once again, this is going to be a two-part process. So with the system off, you're going to want to start by cleaning the heat exchanger, using the manufacturer recommended process. The most common ways, once again, are either vacuuming or potentially washing. Air exchange plates require vacuuming, and I'll go over that in a few slides. After you go through that process, you're going to want to check to see if the heat exchanger has any splits in between the individual media layers, any potential shrinkage or missing sections of media or broken seals around the frame. Anything where the device would not operate as it was initially intended. Also, once again, identify the system layout and the fan locations, so you're going to use that to determine the operating pressure. So turn the system back on for the second part of the process, and you're going to follow the same process as we discussed for wheel-based models. You're going to want to make sure that all the cabinet doors are closed and all the bypasses are closed of the unit, and it's operating at standard mode. And you're going to take the static pressures for all the 4 quadrants again that surround the heat exchanger component. If your system, once again, has more than one operating mode, just repeat this process for all the operating modes. So once again, the TC55 document does have a sample chart for plate-based product. The area highlighted red is going to be used again to determine the pressure gradient, and the flows would be used to determine if you're achieving adequate ventilation. Okay, so the inspection part of the process is really used to evaluate any type of remediation that we required to operate the system during the pandemic. So the general condition is going to determine whether or not maintenance or service is going to be required. The static pressures are going to be used to determine whether or not changes need to be made to the fan system in order to achieve the correct recirculation. Once again, and I can't stress this enough, the driving pressure should be from, or the pressure gradient should be from the supply side, the ventilation side of the airstream, over to the exhaust airstream. It actually should gravitate towards that. If after inspecting the unit you find different results, you may want to consult with the ERV manufacturer or design engineer to determine the validity of the reading, and whether or not what could be done to adjust the operating pressures. Really, all the readings are going to be used to kind of confirm the ventilation rate. And if you find the value is different from what you expected or is required, once again, you may need to consult with the unit manufacturer to determine what steps should be taken to achieve the value that you're looking for. All right, so inspection and evaluation may lead to potential remediation of the system depending upon the condition of the system. So let's kind of dive right into that. So what's typical remediation for an energy recovery system? Well, it's usually cleaning. You usually do more cleaning than anything else. Anything outside of cleaning is usually more of a service-related matter. So it would be a broken belt or a motor or something to that effect. I'd also like to point out that all these recommendations and even the cleaning process of the component just isn't a pandemic-related task, but it really should be part of the normal maintenance and operation of these devices. Cleaning the media is going to remove dust, dirt, or any type of residue and biological contaminants from the surface area. And the most common methods performing this task are either going to be vacuuming or washing the media, depending upon the manufacturer's approach. For air exchange energy recovery wheels, if they look like the one that you see in that left-hand picture, we recommend that you wash the heat exchanger media, as we find that gives you the best result. The media itself is segmented in design, so you can remove the transfer segments from the wheel frame, and you can wash that in a soapy solution. The benefit of the soapy solution is it allows you to get a nice deep clean of the heat exchanger surface area, and also provides a hygienic approach as you wash the segments outside the HVAC unit, and you don't run the risk of introducing any potential contaminant into the airstream. Okay, so to quickly demonstrate that process, I've had some luck with this video showing, so hopefully it works for you all. But this is how the segments get removed. The heat transfer media is actually held in through a series of clips in the unit itself. You would just unlatch those clips, and the energy transfer segment gets removed. You will just put it aside and then kind of repeat it for all the subsequent segments. Okay, so once the segments are removed, what are the additional materials you're going to need? Well, you're going to need a large container, and feel free to use this chart on the left. It's on our website to determine what the relative size of tub you're going to need. You're going to need a non-acid-based coil cleaner or any type of standard, dish soap or detergent. You'll also need access to a water and hose, a soft brush or a vacuum to remove any embedded or lightly embedded dirt, and a flathead screwdriver and an Allen key. So it's a pretty simple process. Once you have the energy transfer segments removed, the process of cleaning them is pretty straightforward. You're going to want to brush or vacuum the surface area to get any heavier residue off the surface. You mix a solution of either the coil cleaner detergent in the bucket, and then you're going to want to fully submerge the segments in the solution. Now, by fully submerging the segments in the solution, it allows the cleaning agent to fully penetrate the heat exchanger surface area. And the best way I can describe this is, you remember those old Dawn commercials where they put the dirty dishes in the sink and stuff starts lifting off them? I mean, that's essentially what you're hoping to accomplish here. The typical rule of thumb is the longer you can let them soak, the better the clean is going to be. So depending upon how long it's been or how dirty it is, the longer you can soak, it usually provides the better result. And then after they're done soaking, you just take them out of the bucket, rinse them off really good, rinse them off really good and shake them of any excess water, and then you put them back inside the cabinet. So the cleaning process for the air exchange plates is a little different. For the plates, we don't recommend that you wash the media, that you just do a dry cleaning using a vacuum. You're going to want to gently brush and vacuum the surface area, and while taking care not to exert too much pressure, because you wouldn't want to damage the device. And just like the wheels, we recommend that you take the component outside of the cabinet to perform the cleaning process, as it's going to provide a more hygienic approach, so you don't introduce any potential contaminant into the HVAC stream. Okay, so aside from the inspection, evaluation, and cleaning of the system, what are some additional mitigation steps that you could take to further improve the system for operation during the pandemic? So in epidemic situations, it's generally recommended to increase the outside air ventilation to the maximum allowable that you can get, to get as much dilution as possible during this time. With that being said, you want to do it without losing control of the space conditions, which would have a negative effect on occupant comfort. So in certain situations, this may or may not be achievable depending upon the design of your system. So it's always good to check with a design engineer or the original equipment manufacturer to determine if this is possible. For units equipped with air exchange energy recovery components, increasing ventilation and filtration may be possible through a process of what we call segment swaps. And I'm going to discuss this in the next slide. But once again, when reviewing this, beware of the system effect that's going to take place prior to making any operational change. For ERV systems equipped with demand control ventilation, I mentioned this before, you're going to want to disable that. So DCV always works to minimize ventilation flow, which is kind of counterintuitive of the guidance that we're receiving for operating in the pandemic situation. For ERV systems that are equipped with economizer, it should already be doing this, but it should check to make sure that the ERV's operation is interlocked with the economizer operation. And then when you go into economizer mode, that the air is being properly bypassed around the heat exchanger. Okay, so if replacing, if you're upgrading the filters or replacing the filters in the system, and you're going from a lower MERV rating to a higher MERV rating, you have to be acutely aware that this is going to change the pressure drop in the system. So by not making any fan changes and just increasing pressure drop, it's going to typically minimize airflow due to it. So therefore, fan adjustments are most likely going to need to be made in order to accomplish or make the system capable of the increased pressure drop. If you're evaluating a unit that is ASHRAE 1060 certified, you can use those ratings in addition to the site recorded pressures that you're recording on that particular unit to determine what the relative leakage is and determine if the pressure gradient is adequate for the operation. Most energy recovery devices do have a seal system that is adjustable, so you want to make sure that you can maintain it over time. Upon inspection, you may need to either adjust or replace these seals to minimize potential recirculation. Once again, refer to the manufacturer's recommendations, instructions for performing that process. And there's been discussion about adding a purge. Now, not all systems are shipped with a purge, and not all systems are required to have one. In many cases, an energy recovery device can work within the ventilation standard without having a purge at all, and that's perfectly adequate because the system's providing proper dilution. Adding a purge to a system that was never equipped with one will have an impact on the operation. The dynamics of the system is going to change. So you're going to want to check with an HVAC engineer or the equipment manufacturer to determine if it's required, or if the system is even capable of doing that. Okay, so if during the process of inspection and evaluation, you determine that you do have an air exchange energy recovery wheel. So this particular design does offer some unique benefits while operating in the pandemic environment. As I mentioned, probably ad nauseum now, that ventilation and filtration is part of the core guidance from ASHRAE and CDC. However, it's often difficult to make those changes to an existing system. So one thing you may want to consider when looking at this approach is utilizing what we call segment swap to achieve either higher airflow, higher filtration, or maybe even a combination of both with an air exchange equipped system. The air exchange segments are interchangeable, and we offer three different varieties which have that have either a higher efficiency segment, a medium efficiency segment, or a low pressure drop segment. So as you move from the high efficiency segments down to the lower efficiency segments, it allows you to either move more air across the heat exchanger surface area or achieve a lower pressure drop to compensate for some higher filtration. So looking at that example on the left, starting with a unit that's equipped with one of our high efficiency segments, if you were to move to a lower efficiency segment or the medium efficiency segment, you'll gain about 0.36 inches worth of pressure. Now, that gain in static, could allow you to move more air into the system, or it could help you with the transition from what your typical MERV 8 filter to a MERV 13 filter. If you're going from the high efficiency segment to the low pressure drop segment, it gives you even more allowance. So you may be able to do a combination of the bunch. I will say, as you go from a high efficiency segment, as you start going into the other segments, there is a subsequent loss of performance. And you want to take that into account when looking at the system impact. However, due to the lower occupancies that we're seeing inside spaces these days, the higher efficiency gains may not be required because you don't have as much load on the building while you're operating the device in the pandemic period. And then once you move out of the pandemic period, you can go back to the normal operation. So it's something that's kind of unique to us. If you have any questions or want to discuss that further, I'd be happy to have that conversation with you. Okay, so I threw a lot at you, and I'll be honest with you, there's a lot of information out there. So here's the sources that I used for this presentation. Starting with ASHRAE, CDC, the Harvard Healthy Buildings website. They all have really, really good information. If you have an opportunity, I highly suggest you check these sources out. I can send this out to you if you're looking for the specifics that I use for this discussion. There's also Air Exchange. I highly recommend you go to our website. We have a lot of documentation as well as useful videos that help you operate and maintain these devices. So if you find that if you have an ERV system and that ERV system is equipped with one of our wheels, we do have tremendous amounts of instruction and quick videos to kind of get you to a point where it's operating at its peak capacity. With that being said, I think I'm at the end of my presentation here. Here's my contact information. Feel free to reach out to me. We definitely want to help folks who have these devices during this period and post-pandemic periods as well. So ventilation is going to be something that's going to be a topic of concern for a long time to come now. So we're here to assist. So with that being said, I'm going to pass this over to Billy, and hopefully you have some questions that I can answer. Thank you very much.
Thank you, Chris. The first question is, in the resource that you sent, that you have in the presentation, is there a link to ASHRAE's recommendations for ERV during COVID?
Yes. So if you go, Billy, is this presentation going to be made available to the attendees?
Yes, it will be.
Okay, so that link is actually, if I still have access to move it back, that link is actually, I don't know if I have my pointer here, but that link is this one right over here. I don't know if you can see that or not, but I think it's the third link in there that they can use.
All right, thank you very much. When you're doing the inspection, what is the PPE requirement?
Okay, hold on a second. I'm going to turn you off just a little bit because it's a little quiet here. Would you mind repeating that one more time?
When you're doing the inspection, what is the PPE equipment that's required?
I mean, typically, the PPE equipment that's suggested in the TC5 document is your standard PPE equipment. So it's masks, gloves, eye protection, as well as providing adequate ventilation to the area, especially if you believe it's been exposed to virus-laden aerosols. So typically, you're going to want to ventilate the area prior to going into it. I will say that energy recovery equipment, especially wheels, it's a mechanical device, so take care to protect yourself against any type of electrical shock, as well as any sharp metals that are within the cabinet itself.
Okay. Is the PPE requirement different for the cleaning versus the inspection?
No. Once again, the general, rule of thumb is to, hands, eyes. You're not using any caustic chemicals to do the cleaning process. But once again, if you believe it's been exposed to virus-laden aerosols, you're going to want to ventilate it prior to working on it. So, try to, ventilate it and give it a little time to disperse before going inside the cabinet.
Okay. And someone asked if you could go back to the screen with your information on it.
Sure. So there's my.
Okay.
I can kind of
thank you.
If that's what you'd like.
Yeah, that's what people are asking, so they can write this down. But all of these slides will be provided. I'll provide a link in the follow-up email that you'll get in the next couple of days.
Great.
Okay, next question is, do you know if get here to the right one here. Does ASHRAE CDC have any guidelines for the effectiveness of the use of UV during COVID-19?
UV, I know, upper air UV, there's been a lot of discussion on that. It's been used for a very long time as a way to disinfect air and control mold growth. So there's been a lot of study on that. There is some narrative from the core recommendations using UV. The UV that I've seen being discussed is not necessarily used in conjunction with energy recovery, but more in the general recirculated airstream. So, once again, I would refer back to the original documentation that I provided. But yes, there is some narrative right now for using UV as a means of virus mitigation.
Okay, there's another question on the same line. Is there a pre-treatment you can apply to recovery wheel components before disassembly?
I guess you could go back to the original equipment manufacturer to determine if you can spray any type of disinfectant on the material itself. It's the most of the documentation that I'm seeing today is mostly concerned with the aerosols and being an airborne virus that you get, and it seems to be less and less. I see these days saying that you can get the virus from picking up something where the virus was deposited on it. So, more than likely, I think the ventilation of the cabinet before sticking your head in there obviously would probably do the best. But yeah, you might be able to contact the original manufacturer just to see if spraying some sort of a disinfectant or something like that before touching it, that would provide an additional benefit. But I'll be honest with you, I seen, when the pandemic first started, everyone was saying, oh, disinfect everything. It seems to be less and less that, and more these days relying on trying to minimize the concentrations of aerosols that are in the air.
Okay, we have time for one more question. And the question is, during your soaking segment, longer is better, but would you please provide some typical times, or what is your soaking time requirement?
Oh, sure. Schools and educational spaces usually have pretty clean airstreams. So, when I say longer is better, I would say in educational spaces, the dirtiest airstreams that I come across, and I'm not picking on anyone, it's just history tells me this, is usually dormitory applications. Those heat exchangers have a tendency to get dirtier and foul to a greater extent than heat exchangers that are just serving classrooms. So typically, I would say, maybe 5-10 minutes soak for your, your typical classroom heat exchanger. You'd probably be looking at more maybe like a half an hour if it was in a dormitory, to kind of really loosen up any type of, tars, aerosols, anything that's really sticky that was in the air, that would get deposited on the wheel itself. In correspondence to that, you would also look at to see how much industrial pollution you have in your area. If there's if your school is located next to a major highway, sometimes that will cause the heat exchangers to dirtier or get fouled at a quicker rate. So, you'd have to make a determination based upon, the quality of the air that you're going through. But typically 15 minutes to an hour is usually more than adequate.
Okay, thank you so much. And as we scroll through the rest of our slides here, I want to thank Chris for taking time out of his busy schedule to do this webinar today. And I want to thank our attendees for taking their time. So until next week for our next weekly webinar, be safe, stay healthy, and have a great day. Thank you so much.
Thank you all.